Okay, good morning. Welcome to this SCANVAC webinar. We are talking about today overheating control needed in Nordic dwellings. And my name is Risto Kosonen from Aalto University, Finland, and I'm also SCANVAC president. And it's my great honor and pleasure to share this session today. So, couple of issues here. Afterwards, we will publish recording and presentation in SCANVAC webpage, so you will have it, all of them. So don't worry, all the slides, all the recording is available there later. And other thing, because we are a lot of people here, I recommend there you put your comment and questions in the question and answer chat channel. And in the end of this seminar, we will go through them and we have chance to discuss with all the speakers afterwards. So today the program is that we have three presentations here. We talk about the situation for existing building stock for Finnish side. Juha Jokisalo will talk about that. Then we have Dennis view for the future overheating risk when we have a current code department, and then finally Thomas Olofsson Sweden will talk about intelligent human building interaction lab for investigation of energy efficient measures. So this topic is quite urgent in the Nordic region because the climate is warming 2 times more rapidly than in average in Nordic area, and if we go for the Arctic area, it's even 4 times more rapidly. So that's why I think we have not really prepared in our building stock, and it's very urgent issue in the apartment buildings when this overheating issue is quite urgent. So I would like to ask the first speaker, Juha Jokisalo, to start and talk about overheating risk in the existing building stock in Finland. So Juha, screen is yours.
Okay, thank you very much, and good morning. My name is Juha Jokisalo. I'm working as a senior scientist in the HVAC group of Aalto University. And let's discuss first about summertime overheating in existing building stock. We have studied that issue with Asin Farahani and Risto Kosonen. This presentation focuses on 3 research questions. First of all, how high are the actual room temperatures in summer in Finnish apartment buildings? How significant is the proportion of apartments that overheat? And how the year of construction or size of the apartment affect the actual room temperatures. We have 4 climate zones in Finland, and this study focuses on Helsinki region, which locates in climate zone 1. Here we can see all the 4 climate zones, and now we are focusing on the southern Finland. This map shows the average number of hot days during 30 years period. And in Finland, we define hot day as a day which daily temperature exceeds 25 degrees. So this map indicates that the average risk of overheating in building is highest in the studied climate zone 1. As we all know, summers are getting warmer and long heat waves are becoming more common. This figure shows degree hours above 20 and 25 degrees during 25 years period in the studied climate zone. So we can clearly see that there is increasing trend in the degree hours. So summers have really become warmer. And in addition to that, also long heat waves have become more common. So here we can see top 5 list of longest heat waves in climate zone 1. And 4 of them have been during the last 15 years. Here, now in this presentation, I use definition for heat wave, which is a period of consecutive hot days. We got access to extensive indoor temperature measurement data for apartment buildings, and it contains hourly indoor temperature for several summers. And in this presentation, I used 2 summers, 2020, which is classified as normal summer. It has 16 hot days in total. And then the other summer is 2021, and it is classified as a hot summer. It has 30 hot days in total, and it was third in this top 5 list that we looked at before, with 16 days long heat wave. So this data contained over 500 buildings per summer and over 6,000 apartments. And the construction year of the buildings and floor area varied a lot in this data set. And the indoor temperatures measurements were carried in a way that one IoT sensor was installed in an entrance hall of each apartment. So it means that the measured temperature describes the average temperature of the apartment. This also means that there can be higher room temperatures as well in the studied apartments, but we use the average temperature now. About the dataset, so we knew the location, year of construction, and size of the apartments, and there are no permanently installed cooling devices. But there were many things that we didn't know. For example, orientation, window areas, number of occupants, how occupants behave, do they open windows or not, and are there portable cooling devices. We carried out grouping of the apartments by the design year, and we classified the apartments to 5 design year group. And the first one designed before the time of the Finnish building code. And in that group, so the ventilation system is either natural ventilation or mechanical exhaust. In the second design group, so there were requirements for the thermal insulation level of buildings in force, and in those buildings there is mechanical exhaust ventilation in use. In the third group, there were tighter requirements for the U values of windows, and it means that the use of the low emissivity windows became a standard solution. So it means that the solar shading of these windows were better than before. And also requirements for the ventilation heat recovery came into force, and then the type of the ventilation was mechanical balanced ventilation with heat recovery. In the fourth group, there were tighter U value requirements in force, And in the fifth group, designed after 2012, so there was requirement for the summertime indoor temperature, the design phase. And it states that simulated indoor temperature during the summer period cannot exceed 27 degrees more than 150 degree hours. And here we can see the number of apartments we analyzed by the design year and size, and these are the apartments after pre-processing and cleaning the data set. And we can see that the most common design year group are the first and the second one, and the 2- and 3-room apartments are most common in the dataset as well. Also, let's check briefly the Finnish requirements for the indoor temperature. First of all, we have housing health degree, and it states that the indoor temperature outside the heating season can be maximum of 32 degrees, which is defined as a maximum action limit. And for the special groups, this maximum action limit is 30 degrees. And special groups are, for example, elderly people in the home care. Then we have 2 degrees of the Ministry of Environment. The first one states that the maximum design temperature of room temperature outside the heating season is 27 degrees. And then we have degree that I mentioned before. So it applies buildings in the design phase and in the building permission before getting building permission. So the simulated indoor temperature should fulfill the requirement, and it should not exceed 27 degrees in the apartment building more than 150 degree hours during summer months, simulated with fixed input data and the test reference year. So this test reference year has been done for heating energy calculations, and it describes average weather conditions, and it's not that suitable for this kind of overheating simulations because it has only 7 hot days in climate zone 1. Okay, then let's go to the results. And here we have a duration curve of indoor temperatures of all measured apartments during the hot summer of 2021. And we can see that the range of the temperatures is really high. But from action limit point of view in the housing health degree, so we can see that the higher action limit of 32 degrees is exceeded in 4% of the apartments, and the lower action limit in 32% of the apartments. And the design criteria of 27 degree is exceeded in almost all the apartments. Then how different is the overheating during the normal and hot summer? Here we can see the proportion of apartments above these chosen temperature criteria. So we can see that most apartments exceed 27 even during the normal summer. And both action limits are also exceeded during the same normal summer. And if we apply this kind of results for whole apartment building stock of Helsinki area, which means over 500,000 apartments, and we assume that they behave similar way than these measured apartments. So then the higher action limit would be exceeded over 6,000 almost 6,000 apartments in the normal summer and over 20,000 apartments in the hot summer. So even if this percentage of 1 and 4% sounds quite low, but the number of apartments would be quite significant. Here we can see day and night time difference in overheating. So for all day and relaxing time, and these figures shows that there is only minor difference between the all day and night time. So the load-bearing structures of these measured apartment buildings are brick or concrete, and if such apartment buildings warm up, so they will stay warm even at night. Then how long will the apartments stay warm? So this table describes that. So it shows the percentage of apartments which are continuously from 1 to 7 days over the temperature from 27 to 35 degrees. And for example, if we look at the 27 degree, then this result indicates that there are 85% of the apartments are continuously over 27 for 1 day, or 7 days in 47% of the apartments. So this indicates that once the massive apartment buildings warm up, so overheating takes a long time. And we have also seen from the data that even if the heat wave is over, so overheating continues a long time after the heat wave in such buildings. Here we can see the effect of design year on overheating in the normal and hot summer. So here result shows that the median value of degree hours above 27 degrees is highest in the third design year group in both summers. And this is quite interesting result, because in those buildings, so the windows are better than before. So they have better solar shading than in the design year groups before them. But also ventilation heat recovery requirement came into force. So that may have a positive effect if it is so, for example, that the ventilation heat recovery is not accidentally bypassed during the summer period. So we don't know that, but that could happen. Also, result shows that the fifth design year group is warming less than the other buildings during the hot summer. So it indicates that this requirement of summertime indoor temperature is unable to fully prevent overheating, but it has positive effect, so it reduces it slightly. Here we can see the effect of apartment size on overheating, and here there are degree hours above 27 degrees in both summer and the floor areas are classified into 3 groups, and the results show that the smaller apartments are warming slightly more than the others. So this is quite expected result. Okay, so then this study showed that the Finnish apartment buildings overheat significantly during the hot summer, but they also overheating during a normal summer. And once massive apartment buildings warm up, so overheating typically takes a long time and with minor difference between day and night time. So, and also the summertime indoor temperature requirements have succeeded in reducing overheating, but not yet enough. And it means that the stricter regulations are needed to prevent overheating in new buildings. And which is more challenging, more attention should be paid to prevent overheating in existing buildings. If you are interested, there is more information in a couple of our papers, so details can be found there. So thank you very much.
Okay, thank you, Juha, and I think we are on time. There is just one question here. You focusing, Juha, on the apartment building. Here's one question about that. Is there in Finland requirements to carry out simulation design phase all type of buildings?
Yes, so there are. So this requirement applies, dimension applies for apartment buildings, but there are also requirements for other buildings, and they are more strict. So temperature level is 25 degrees, that they should not exceed this 150 degree hours. Detached houses are excluded in this requirement, but other building types should be simulated.
Okay, thank you, Juha, and I think we can move on for the next speaker. Steffen Petersen will talk about in Danish situation, what there. And once more time, I encourage you to add your questions or comment in the chat, and we can talk that in the later. So Steffen, screen is yours.
Thank you very much, Risto. It's a pleasure to be here, and thanks for the invitation. So my name is Steffen Petersen. I am a professor of building science at Aarhus University in Denmark, and I'm here to talk a little bit about a presentation that I also gave this summer down under in Australia, so on the underside of the planet, where we're also talking about overheating issues. I guess we're talking about that everywhere. So this is recycling of some material, and that's also a good thing, I guess. So first of all, I brought this little map of historical temperatures in Denmark, and how the spatial distribution of that is in a small country like Denmark. We are super small, but there is a little bit of variation across the country. And I basically also just brought this map to show you that Aarhus is right there. So that's where I'm situated right now. But anyways, this is a talk about what's going on in Denmark when it comes to overheating of existing buildings, and the way that we design new buildings today. Because the thing is that we are designing buildings for the future, but we are designing them based on past weather. So the way in the code is in Denmark is that we have a requirement that says that in rooms where people stay for a longer period of time, it must be ensured that a thermal indoor climate that is satisfactory in the terms of health, comfort, and can be maintained during the intended use and activity. And that is the paragraph. That's the requirement, and as you can see, it's not super easy for designers to work with, especially those who want to quantify things. But there's nothing else than this in the requirement. But there is some guideline how this requirement could be fulfilled. And it says nowadays that the operative temperature must not exceed 27 degrees for more than 100 hours a year and 28 for more than 25 hours a year using the Danish reference year. So this is a simulation requirement. So you model your building design, and then you do the thermal simulation, and then you have to use this design reference year, which is a reference year that is structured from data. You can see my pointer from weather data right there at an airport. So for whole Denmark, all buildings are designed as if they are lying at this airport. And we have been doing that for 50 decades or something like that. So that's the way that we do it in Denmark at the moment. And the question is that resilient when we look into the future and what happens potentially with climate change? So the current building design in Denmark is something like this. This is just to have some pictures up so you can have an idea about what's going on building design-wise in practice right now. These are all fairly new apartment buildings across different towns in Denmark, and you can see they are quite alike across the whole small country, which makes sense because they're all designed for the same weather data file. And Denmark is also rather small, so why would there be a variation? Single family houses is something like that. You can like it or you cannot like it, but this is what people are building. For me as a building scientist, I think it's weird not to have an overhang in a wet country like Denmark, but this is the modern way of doing it apparently. The question is, in this talk and in this paper that we made for this conference is, would these buildings also fulfill the code moving forward when we are projecting weather data into the future using different climate change scenarios? So we're not completely sure what is going to happen, so we have to do scenarios. And here is the small country of Denmark again with different climate change scenarios. Up here it's the RCP 2.4, so a very optimistic development of our temperature, and RCP 4.5, which is kind of a mid-road thing. And then the most likely one, unfortunately, is the 8.5, which is down here in the bottom. And then we look ahead in the future from 2030 to 60, and from 50 to 80, and so on out into the future. And you can see the number of cooling degree days are increasing significantly in the most likely scenario of climate change in Denmark. But you can also see that there are some geographical differences in a small country like Denmark. So this thing that we are designing buildings as if they are in an airport near Copenhagen, well, maybe that's not the way to do it. And maybe we should look into the future with the increasing cooling degree days. So our question here was that, are Danish dwellings built today resilient to the risk of overheating, assuming different climate change scenarios? So the method that we used for this was to say, okay, let's make some parametric models of a living room in a dwelling, and then use an algorithm to generate a lot of variations for these building designs. And then we have developed this tool that we call IceBear. It's a parametric, easy to use thermal calculation tool. And then we simulate the performance of these 11,886 variations using sampling from this table you can see over here to the right. So we get different geometries, different combinations of heat capacity and heat conductivity, and so on and so on. And then after that, we evaluated how many of these would pass this criteria of overheating I showed you earlier with 100 hours above 27 and so on. And a total of 4,115 passed that. And we could then condense that to 321 models that kind of represents the whole sample of these 4,150. So we get this these designs that fulfill the criteria today using the weather data file that the building requirement says that we have to use. Now, the interesting thing would be to see if these buildings would still fulfill this overheating requirement when we use climate change scenarios. So we take these 321 models and then we put them into these 3 RCP scenarios I showed you earlier, and we do it for the different periods ahead in time. And the question now becomes how many of these models that are allowed to be built today, because they are not overheated according to the Danish building code, but would they be in the future? Would they pass the guideline for overheating using other weather data? So for this purpose, we also chose a few geographically spread locations in Denmark. You can see this on this cooling degree map, Aarhus, where I am at right now. And then we have basically the 5 largest cities in Denmark, which for some interesting reason also are situated in different degrees of increase of cooling degree days. So we have a geographical spread, and these cities are also the largest ones, so this is where it might impact the most people. So we are also simulating them for these different locations in Denmark to see if there's some spatial distribution of the problem. So here are the overall results, and I'm sorry, it's a lot of data in a table, so I'll just block some of it out, so it's maybe a little bit easier to understand the development here. So we have the different cities over here. We have the RCP scenarios here, and I'm just highlighting only the 8.5 so we can see the development over time. So these are the periods ahead in time. And you can see this, for example, here for Copenhagen. If we look ahead in time, there's only, you could say, 249 of the 321 designs that is fulfilling the building code requirement looking into a near future. Looking further ahead in time, none of them will fulfill the code. They will be overheated according to the code. If we go to a different location, Aarhus, where I am at, we're looking a little bit ahead in time, all the designs will fulfill the code, and then in the future, some of them, but in the far future, none of them. And so on. You can see the development is slightly different across a small country like Denmark, where we can see depending on how far we look ahead in time, these designs will not fulfill the requirement in the current building code. So what can we do about that? What is actually important now to think about when we design our buildings moving forward? So we just looked into the features of these simulations to have a look at those who are fulfilling the requirement. What are the traits? What are the design features of those? And here is the number of complying designs out of these 231 sorted by heat capacity. So light, medium, and heavyweight, you could say. So I'll just highlight the 8.5. And here you can see, okay, so looking at, let's just say Aarhus, there is a tendency that there are more designs fulfilling the criteria, the more thermal capacity they have. And that combined with night ventilation in Denmark, because the nights are relatively cool, is actually a very, very efficient way of minimizing some of these overheating hours. So it makes sense that heat capacity, the buildings that are built today with the most heat capacity also have the most potential to kind of mitigate any climate change. And that potential then decreases the number of dwellings looking ahead in time. Is less and less features in this, and looking ahead far in the future, none of the buildings are fulfilling the requirements anyway, so it doesn't matter if you have high or low capacity in this end. Well, there's one design that is fulfilling. That's maybe a very interesting design that we will have to look into. But as you can see, there's something about heat capacity that we should think about moving forward. Another feature here, let me just block these out, is whether the windows have overhang or not. So do they have a local shading, you could say, over the window in the form of overhang? And again, you can see that there's some development that with and without, so you have with and without, it seems like an overhang is also a mitigating way of a mitigating feature for building designs in the future. All this might make sense to many of us, but this is just showing the data from a study like this. So here is with and without shading from surroundings. So do you have, are you in an urban context or not, basically? Again, looking into this, it seems like, okay, if you have some shadings from the surroundings on your buildings, it seems like they have a stronger resilience towards the overheating potential. Again, because the sun is also governing a lot of the indoor temperature in dwellings in Denmark and in the Nordic in general, I would say. We shouldn't underestimate the sun in this case as well. It's not only outdoor temperature. Yes, orientation north-south. Again, there's a little bit of an interesting thing here depending on the location. It's actually not so much, of course, it's better to have it towards north, but it's still possible to have south as well, unless, of course, we look far into the future, then something else might happen. Let me check. 2 or 3 layer glazing. That's always a discussion in Denmark. Should we have 2 or 3 layer glazings in our buildings? It's, as you know, a trade-off between heat loss and heat gains. So the 3 layer glazings, they reduce heat loss, but they also reduce heat gains because of the G value, and it's vice versa with the 2 layers. So what's the nice balance in a Danish context? So again, looking at 2 layer versus 3 layer, depending on whether it's facing north and south as well. We can see some statistics here showing that it depends, I would say, but it's not clear whether it should be 3 layer glazing or should be 2 layer glazing. It very much depends, which I think is interesting, and also opens up for further investigations into what would actually, when we take into consideration daylight, for example, what is then the interesting features and the appropriate design choice for glazings. Glazing areas. So how large are the glazing areas in the models that fulfill the criteria? And they vary a little bit around a number. So it also shows that there is some variation. There's some design opportunities in terms of the glazing. All this is, of course, connected. Area of the glazing, the orientation of the glazing, U value and G value of the glazing. It's all about solar heat gain, you could say. But there are some options. There are some ways that could help in terms of thinking about how do we avoid overheating in our buildings for the future. So our conclusions from this little study here was that there's an urgent need to revise the Danish building code regulation to account for future climate conditions, as many current dwellings designed will fail to meet overheating criteria in the future. So that's definitely our notion based on this analysis. We also see that thermal mass, window overhangs, and shading from surroundings can mitigate the issue. So there's a little bit of advice for building designers included in this study. Building codes should be updated to encourage climate adaptive design strategies and passive cooling measures. So they don't at the moment, but maybe we should guide a little bit more. Update of thermal comfort evaluation method for dwellings as well. I don't think counting hours about a certain threshold is an appropriate metric for dealing with overheating. We have other metrics that I think are more appropriate, so we also should look into that. The final thing I have is just a little commercial for a draft paper that we are doing here. You can see our nice Nordic region. I'm sorry Iceland couldn't be on this map, but we have done this recently and are trying to publish this at the moment. You can find it online already. But this is the development of cooling degree days and heating degree days across our wonderful Nordic region. And we can actually zoom in on this map and see what's happening in a grid of 12 times 12 kilometers when it comes to this heating degree day. We're also looking into the length of the heating season and cooling seasons, how long are they and how much do they change and where do they change? So there's a little bit of data here that is not only relevant for us Danes, but maybe also for our dear neighbors in the Nordic countries. So thank you very much for your attention. That's all what I had for you.
Okay, thank you, Steffen. And I think that okay, wait, there's one question here. Maybe I can ask now that for that is a question about, is the passive cooling methods enough to handle in the future climate, or do we still need it to think about mechanical cooling?
That's a good question. It all depends, I guess, would be the right answer for a building physicist as me. I think we can mitigate a lot in Denmark still from using ventilative cooling, but we do have to look into more efficient mechanical cooling, especially for our office buildings. That would be my short answer.
Okay, thank you. Maybe we have to move on and we can come back for the questions in the end of the session. So Thomas, screen is yours.
Okay, thank you very much. See if I can share my presentation here. And it comes. So, yeah, thank you. Can you see my presentation?
Yes.
Yeah, thank you. Yeah, so my name is Thomas Olofsson and I work as a professor at Umeå University, and today I will introduce a little what we are doing in our lab, which is kind of dedicated for studies of energy efficiency measures, but it is very relevant also for today's topic, and I will show both how we are working, but also results from a couple of studies, and also introduce a future study we are starting now. And the results I'm going to present should be acknowledged very much to my colleagues. It is Rachel Liu, who is the director of this Intelligent Human Building Interaction Lab, Callum Feng, who is an assistant professor doing a lot of the work together with Juha Jokisalo, who is also the staff scientist leading the lab. So this is the team that should be acknowledged. And well, today we talk about overheating control needed in Nordic dwellings, and the perspective we have in our group and what we are working with, that is that we have a climate change going on, increasing temperatures. We can see the effects all over the world. There is a transition also going on from fossil fuels to renewable energy. That is something influencing us. It influences the production and distribution of and use of energy. The industry sector are influenced, and also, of course, the transportation sector and the building and service sector. And also everything are happening in the same time, and we are all influenced by each other. So the profile of what the research we are doing is that the building sector has a major impact on this transformation, but also and the use of the planet resources, of course, but we also have to adapt to that these changes, and that is also the kind of topic for today. We looked, it was interesting, we had the previous presentation, we have seen a lot of maps, and if you look to the left here, we can see that the temperature degrees, the increase of temperature is going rather fast. And these are data from 2014, and we can see we are located in the north of Scandinavia, near the sea, in the Baltic Sea, and we can see that, well, we can have a lot of effect of this increased temperature. And we can also see on the left map that is little similar to the data we saw from Aarhus, and we have, or from Denmark was it, that here we can see how the length of the heat periods or the heat waves are increasing from now and based on then in future climate scenarios. Another thing is also in northern Sweden, the buildings are adapted for short heat waves, for a colder climate, and this happened very fast. And we can also see that the heat waves especially in the north, are especially kind of increasing fast relatively also to others. And how will we meet these future climate changes, and how will we adapt both the use of buildings but also the built environment? So that is a little what we are studying, and I will present. And the background is a little about how should we investigate and study this. And well, we can do a lot of simulations, of course. They are very powerful simulations to study these effects of climate on the adaptation and how we should construct building in the future. Well, we can also work a lot with surveys and interviews. That is very useful. There are a lot of living labs happening now where we can do this kind of studies, including users and different kind of technical innovations. And what we are doing is another approach. We have what we call an intelligent human building interaction lab to get other kind of data and other opportunities. And what we can say about this lab is that what is kind of the key thing about it is that it's a physical environment and it's also a virtual environment in the same time. There is people sitting in the lab, they can experience the physical feelings of different scenarios, but they can also be having experienced different virtual scenarios in the same time. I can show that later. And then we can study climate change, and we can also from that we can study how the people adapt to different climate change scenarios, physiological and effects, psychological effects, and also based on this building upgrade. And I can show you one example here. We have a film here. And in this film, that is an example how we are working in the lab. We have one person sitting in the lab and doing some physical work. And in this lab, the person can also experience, report how, if it's cold and cold, what hot and cold, warm and cold. And you can also experience, write down their experience, but they can also make different changing different kind of conditions, for example, heating, cooling, and so on. With this lab, we can now investigate building stock, different building stock conditions, and how this building stock will both how the users in this building stock, how the behavior of the user in this building stock are influenced by different technologies. And we can study that also in different climate scenarios. So we can go from a more problematic future scenario to a more green scenario. That is what we try to say with this one. Now I will come to my first study to illustrate some of the findings of what we have been doing. And this first little study I will show to you is from Umeå, and we are studying two nearby areas. The area A is an area with more multifamily buildings, a little lower income area, older buildings, and area B is single family buildings with another kind of users, with another kind of quality of the buildings. And then we will study how the climate resilience differs for these different areas. And to do that, we collect a lot of data. We collect data from that the government has collected in different surveys, and also the databases from the Swedish Building Energy and Technical Environment certificates, which we have. We have GIS data, but we also have data to the down right corner that is more based on previous research, where we have collected and merged different databases together to have more property building data information. And based on this data, we can have different kind of attributes of these buildings in this district. We will know the building type, the housing area, the orientation, ventilation system, U values, geometry, window wall rate area, heating system, occupancy, and light. and so on. And they are also collected from that. And that is one part of it. The other part of it is that we can also, in this data source, we can also from our lab collect behavior data. And this behavior data that they can be collected from our lab, which is a lab where you are, a person can stand in the lab and virtually experience different kind of building technologies, building environments, and also be provided the physical experience of that, as I showed in the short film, and can report the experience from that and how they will act. And what we are doing in our model here is that we are merging this kind of building big data to the right upper corner together with this occupant behavior collection from the lab. And then we are merging that to what we call a data augmented model, where we are, based on simulations, can merge this kind of behavior data with the building technical data to get information to this kind of data augmented archetypes. And I can show you for an example what that can show. For these two areas then, we have here a diagram showing how the buildings will perform for a current situation and for 4 different future climate scenario. And if we look, for example, on the current scenario, we can see for the first blue one to the left, how many hours of overheating this multifamily buildings in this lower income district will have, and they are pretty few. The second one is that we have the single family buildings, the larger ones, either with an active window control or a normal window control. And then the red one to the gray one, we can see that we can reduce a lot of heating hours with active window control. And for the larger buildings, there will also be a difference. However, what is rather interesting in this study is that perhaps the buildings that will have the big challenges in the future based on this study for this district is that it is actually the single family buildings that will be rather affected. And perhaps that also the study with the overhang of the windows and how these buildings are constructed, we saw the Danish example, could be one example of many. Perhaps the problematic buildings in the future, at least in district, could be the multifamily buildings, but an active window control can reduce the number of overheating hours somewhat. Another study we have also conducted is that it is more on a city level based on this data and with this method, and that, well, the cities will be very much affected by the global warming in the future. And the interesting thing is perhaps where do we have the vulnerable buildings in the area, and what properties are related to the vulnerable buildings when we think about overheating in the future, so we can know a little more about strategies. And in this data, we have used this big data we have of buildings. We use the behavior model we have, and also the big data multivariate simulation model. And then what we can see on the right here is that we have studied different parameters. For example, we can study operative temperature, we can study predicted percent of dissatisfaction for these different buildings simulated, and we can also, based on kind of a limit when we think it is a problematic situation, we can do that for all buildings. And then when we have this data for all buildings, we're trying to group them. So we have the buildings experience this problem that are identified as vulnerable, then they are grouped as red based on this kind of where we put the limit, and then black is that when they are not. And then we can also study the parameters related to when they are for the vulnerable ones and for the not vulnerable ones. And we do that with a multivariate study, we call it PRIM. And from this modeling, we can cluster buildings, and we've done that for our city. So we have different clusters of vulnerable buildings and different clusters of what we call robust buildings that are less vulnerable to climate change, and the number of based on overheating hours. And then for these clusters, we can also learn a little about which parameters that are related to this, how they are clustering, what is characteristics for these clusters. And I can show you in the map, for example, how it shows for our city in Umeå, where we have done this study, and where we have these clusters geographically spread over the city. And here we can see that the first cluster, the blue one, that is the vulnerable single family buildings in the region, and then we can, or in the city, and then the red one would be the robust buildings in the city based on the data we have in the database and based on this kind of modelings and a multivariate study. And we can also do some simulations with these buildings. We can, for example, study if we have the performance of under different future climate scenarios. We can adapt to this data set and see how many overheating hours will the vulnerable buildings have in a future hot scenario, and how many overheating hours will the robust buildings have in the future climate scenario. And if we look at the top one, we can see that when the yellow is 900 overheating hours and the very red is 3000 overheating hours, we can see that the vulnerable buildings show a much more problematic behavior during the same scenario studies than the less than the robust one in the bottom. And we are also studying for this data, we are also studying different kind of adaptation solutions, and then we can also study, let's say we are applying that adaptation solution to all vulnerable buildings or all robust buildings, and then we can see how that will influence the number of overheating hours in this data set. And we can also see that geographically on the map illustrated here. What we are also doing is that for the future, we are also interested in using our lab more kind of directly. So what we are doing is that we are developing different scenarios for our lab, where we are studying a combination of different air temperatures, different kind of heating, humidity and air velocity climates in the occupied zone. And then we can in our lab we can have people experience these different scenarios, and we will study the person, how the person kind of react to and how they integrate with the technology in the building, how they interact with, if they like to take off the jacket or open the window, and what they're doing. And the kind of interesting thing for us doing this kind of studies is that we can investigate, we can put people in the lab, and we can have different categories of people with different background, different age, gender, and so on. And we can study how they will act in future climate scenarios based on different kind of option scenarios, where they can open windows, or what will they do, and how will they kind of how will they define the experience in terms of hot and cold, and if it's unsatisfied and dissatisfied in this climate. And that is also what we are working on now, and also try to integrate these results in these big data studies to learn more of how future buildings can or will behave or be in the future climate scenarios when they are occupied. Yeah, that is how we are working in Umeå with this one. Thank you very much.
Okay, thank you, Thomas. And I think we have now time to call some questions and comments. What we have it here, we don't have so much here, but you can add it more here. But I think one question here is dealing with this nighttime ventilation and utilization of thermal mass. And I would first ask Juha to tell something about Finnish experience of that, how useful that, and then Steffen, if you continue for Dennis side for that.
Yes, we have carried out other study, so simulation study, and study different how the different measures to project overheating would how effective they are, and one measure is the improving nighttime ventilation during the summertime, and if it is so that additional investments are not needed, so the only unit and the ducting is enough, so then that strategy is very cost effective. It's actually the most cost-effective strategy we have found. So just improving night ventilation. But if it is so that there is extremely hot summer and very long heat wave, so that strategy helps a lot, but it doesn't cannot fully solve the whole issue. So active cooling is needed in addition to that, I would say, in Finland.
Well, I can say it's kind of the same experience we have in Denmark from this, and of course, if it's way too hot outside, it doesn't help open the window. But we see a lot of effect from also the existing buildings. If it's possible to leave your windows open to some extent when you're not at home, so you come home in the evening to a nice and cool building in certain, especially transition periods along the year, but also during the summer. That also has a great effect, and it's very cost effective just to keep the window open. And if you can let it stay at night, it's also good. One issue we have here is insurance for burglary. So how do we make solutions where you can actually have this venting going on when you're not at home? But there's also solutions for that. So I think it's a very effective way of mitigating a lot of this overheating issue. And of course, then when we have extremes, we probably have to think about something else as well.
Okay, thank you. I think then there is a question about this health issue, that what is the threshold value for that? And I think that's we don't have medical doctors here, but maybe we can continue the same, maybe change the order. Maybe Steffen, you say that. What is your Dennis situation for health? And then Juha and maybe Thomas can continue for that. So health
yeah, very short on
what
that.
Is the limit?
Yeah, very short on that. We don't have any. It says in our building code that it should be comfortable and healthy to be there, but they don't set any bar for that. So I actually screenshot Juha's on 32 degrees because I think that's really interesting. I would have to look into that document. So I'm much more interested in hearing from your experience in Finland, for example.
So we have this housing health decree in Finland, and there are those two action limits, 32 and 30. But I have to say that there is no any medical background behind them, so they have been just chosen, and I think there have been discussion in this ministry that they should be updated because they are really high. There is no.
Okay, so they are too high. They think they should be even lower.
Yes, that kind of discussion has been so.
I don't know if you see the same thing as we do, because when we have heat waves, we can actually see that our older vulnerable people above 65, that there's a higher prevalency of deaths during those times, and they ascribe that to dehydration and stuff like that. So in Denmark, you could, in principle, look into those periods and find what's the boundary here. But I mean, I'm not a doctor either, but I was thinking aloud now.
I think it's a little bit challenging because people are different, but that's maybe the other thing. Maybe Thomas, do you have something to add for Sweden's experience for health limit for temperatures?
Yeah, I worked before with health related to sick building syndrome, and I mean, this is a very tricky thing, and I think I see the same here. Connecting health to indoor climate, it is a difficult thing, and I think it's that one should be a little careful, and because we, as you started to say, we are not medical doctors, but I think it's a very important area and to work together to study, because I've seen studies where they put together heat waves and transports with ambulances and things like that, and they may say that perhaps there is some kind of connection here, but one should be careful making the conclusions. But it's an important area to research for the future, I think, and when we as engineers make conclusions, we can go a little wrong, but definitely I think there is a big risk for health in the long heat waves we will experience in the future, in the middle of the summer, when the heat waves are connected for many days, and people can't like open windows and ventilate and that way by themselves, reducing the climate, and then when they don't have HVAC systems. So yeah, an important research task.
Okay, I would like to ask Steffen, you mentioned this, Dennis, you have now the limit 27 degrees and you have 100 hours. It's not the degree hours, it's hours.
It's hours. But then, so if you are 0.1 above, it counts as 1. Okay,
but then you mentioned that some other metrics are needed there. What you could propose here? What kind of metrics?
Well, first of all, I think we need to investigate a little bit more carefully what is actually thermal comfort in homes, and what would be an appropriate way of articulating that. Because yes, we do have heat balance equations of Fanger and can calculate something based on that. But I think you are more forgiving when you are at home, because the investigations we have made in especially in multifamily social housing, I have entered many indoor climates, finding them very poor and bad. But the people who live there love it. They love their home. They love the conditions because it's my home. So you know. As was also said earlier, we are very different, all of us. So I don't think even we have the kind of the appropriate overview of what is actually thermal comfort in a home. That being said, I think we have maybe the poorest one when we're just counting hours above 27. I feel like what you said, like the degree hours would just improve it. So we have a very weird way of doing it right now, and I see further research needed. There are some emerging indexes. We did a paper some years back together across different universities in Europe where we applied different metrics. So there are, but all these metrics are kind of like hypotheses right now. So I feel like we need to look more into what is actually thermal comfort in homes before we can make a criteria.
Okay, here is questions of this humidity level here, that what kind of target or limit we have it here. If you're starting from Juha first here, humidity level in Finland.
Yeah, so we haven't defined any requirement for the humidity level for Finnish buildings.
What about Denmark?
Nothing. I mean, there are some guidelines from the European norms and codes stating be between 30 or 60. You know, that's kind of the rule of thumb, but there's no focus on that. We don't have the big issues with too low humidities in Denmark. Sometimes it might be too high, and we have damp situations in the winter. So it's more like a mold issue thing when we go into that. But from a comfort perspective, there's no requirement.
What about in Sweden, Thomas? Any discussion about humidity level?
Yeah, it is, of course, and as you say, when the heat wave, when we have the warmer heat waves we will have, the more important is this issue with humidity, of course, because that will influence relatively more than. And in our lab, where we are doing our studies, we are providing a temperature comfort, an operative temperature, but also a humidity level. So we are investigating how people are experience the operative temperature and the humidity level and the air flow in the same time for different conditions, so to say. So for us, we think that is a interesting parameter, but we know too little about it, I would say, under extreme conditions.
So is there any, if I somehow this comfort and health issue, any recommendation you would like to say is we should do it now to mitigate the problem? If we're starting from Steffen for Dennis side, what you propose to do it with the existing building stock to improve comfort and health there?
Yeah, exactly. Well, there are different ways or different things we need to do. We need to look into what are the criteria that we need to meet. And then I think we need to, at least in Denmark, start to look a little bit ahead in time at different climate change scenarios instead of always looking at an average period back in time. So it's quite easy, I think, but it's also very difficult because it's rules, and rules are super hard to change apparently. But physics is like what it is. So I think there's a lot of practice that needs to be changed. And once we have changed that practice, I think we have the tools and we have the knowledge to actually mitigate it with the means that we have today. We've talked about shading, we have talked about night ventilation, thermal massing, and all these things. We know this stuff, but we just need to have other boundary conditions when we are, looking into what should we do with the existing building stocks. So that's, I think that's where we need to start.
Okay, Juha, if you add something there.
Yes, so the existing building stock, that's the challenge. It is, I think, passive measured window shading, blinds. I think so the controlling nighttime ventilation. I think those things that are easy to use in practice. But then I would say that for the vulnerable people, so who are sick or old, so I think the apartments they are using, I think they should be equipped with active cooling, because if it really happens that very long and hot heat wave comes, so the active cooling is only solution, and it's, I think, quite cost-effective solution to install cooling air source heat pump to the apartment or detached house.
Anything add, Thomas, here?
Yeah, I think very good comments by Juha and Steffen. And I think that one thing to add there is also, I mean, the buildings are systems where the users are integrated. So how are different users using these technologies? How are different users? How is the variation? You mentioned the vulnerable people. How are they really acting? And I think we have to learn more about that, because we can give them any technical systems, but if it doesn't work together with them, but also learn the difference between different categories of users, more about the users in the interaction with building. That I think is also a key question in parallel, of course.
Agree.
I think here is one comment here is this overheating is not, if I understand right this comment, but it's not only for the summertime, could happen also the mid-season, and I think that's also other thing to discuss. Any discussion that happened, for example, Sweden, what do you have it? Because like in spring, you can have it that some rooms are overheated there.
Yeah, of course. You mean experiences or research results from the periods of spring?
Or target values or some recommendation, whatever. Like in Finnish, we have this indoor climate classification, and we have now focusing quite a lot of wintertime and summertime, but also we have some curve for the mid-season, but that's always very problematic. What is the target value for that? Because it's not cooling, it's not heating season. What we should target it there?
Yeah, I can't say that we have developed anything on that one. I must pass on that because, but of course, this is a very important question. Yeah, I don't think we have done anything more than you.
What about Steffen in Denmark?
Well, in Denmark, it often ends up in some kind of weird discussion because in some of our guidelines, there's a condition for summer and a condition for winter where you have criteria for summer should be between 23 and 26, and for winter between 20 and 24 or something like that. And then the weird discussion becomes, when is it summer and when is it winter? When does that start? And people tend to forget that in our climate, there's long transition periods. You know, what about spring and fall? But we have to set a line somewhere in May saying here starts the winter or here starts the summer. You know, it's a very, very weird discussion to talk about it like this. But in principle, it all comes down to a misinterpretation of a criteria based on heat balance. So the PMV equation, where people this is not about summer and winter. It's about heat balance. It's about the clothing you wear. So if you have a clothing of 1, then they call it winter, and if you have a clothing of 0.5, they call it summer. But it's nothing to do with summer or winter. It's something to do with your heat balance with the environment. So what we are trying to do is say we don't care about summer and winter. It's all about, you know, if you are flexible in your clothing, you have to stay within these comfort criteria depending on that. So more dynamic criteria than talking about summer and winter. That's something that we are pushing for, but at the moment it is this weird discussion about when does summer start and when does winter start. That's the situation in Denmark.
Okay, we still have a time, couple of minutes here, but I think there's some more discussion about this nighttime ventilation here and energy efficient of that topic and how efficient that is. That maybe ask Juha for that in the Finnish experience about night ventilation. How much is consuming energy and what is the effect? If you put some kind of numbers here, if you remember.
Yes. So we have made example simulations and increasing nighttime ventilation, it increases electricity consumption lit, so fan electricity, but that's not much. So it's just a minor thing there, and it really helps. So we have one example building, so the apartment building designed in 70s, and it decreased the degree hours about 25 degrees by 1,500 degree hours. So during very hot summer. So I would say that it's really something. So it doesn't solve whole problem, but it helps in addition to other measures.
So anything add for Dennis or Swedish side?
I think that the problem perhaps is that, well, we haven't designed our buildings to be efficient for nighttime cooling, and I mean we have, and in the future perhaps we have to think more about how to store nighttime cooling and how to design that in another way. So I think there is a big potential here that we probably have to use in future building design. But since that haven't been in the mind, then as it is, like you have said, that the effects are not very good. Perhaps for some buildings, just by luck, they are more efficient. We should learn more about it, and it should be perhaps an efficient measure in the future, an important one.
And I think it's interesting what Juha just said, that okay, so night ventilation can also be mechanical. Just let the mechanical ventilation run, but it comes with the cost of electricity. And we've done some, back in the days when I was a consultant, we designed a school where we looked into, okay, should we have a low mechanical ventilation rate with mechanical cooling to keep the temperature? Or could we have a higher variable air volume ventilation and let it run at night time to avoid overheating the day after? And the economy was better for the latter. So having a slightly larger ventilation unit that could ventilate at night and use electricity for that rather than electricity in the daytime for cooling, that was the best overall economic solution for that building. But it was also designed to utilize the thermal mass for this purpose. So you cannot just, do it. You have to think the whole equation through.
True.
Okay, I think that there is maybe not any other different angles in these comments here, but we are coming in the end. Maybe all the speakers, maybe something which you want to say, which you have not mentioned earlier. If we're starting for Thomas here, what do you want to say, which we don't have discussed here?
Yeah.
Final words.
Yeah, my final word is that for the future, I very much think it's very important that we are studying buildings, that we are also studying more the users, the different kind of effect of different users, the age of user, the background of user, and study how that is. So we are designing the buildings not only for the kind of categories designing buildings, they have themselves in mind. We have to think more about future user categories and how we adapt them to their behavior and their the way of using it. So that is what I think is very important for the future, especially in this perspective of heat waves.
Okay, Steffen.
Talking about transitional periods where it's difficult to know should your set points be and stuff like that, I think model predictive control could be a very good way of starting to navigate the building through those periods, looking ahead in time in weather forecasts and then control the building accordingly, maybe from energy price signals, but also CO2 intensity in the grid and stuff like that. So I think there's some potential in our climates with long transitional periods to utilize more advanced control. So we're also looking a lot into that. I know some of you guys are also doing that. So I think we have a lot of things we could do together here.
And you have something to add. Final words.
Yeah, I would just simply say that we should keep more attention to this hot summers, so to mitigate this issue.
True.
Okay, I think we are in the end. I would like to thank all of the speakers, and also I would like to thank SCANVAC organizations who have been make this possible. Siru Lönnqvist and Anna-Meri Kari behind the curtains had handled this, and also I would like to thank all the participants of this seminar. So afterwards we will publish this video and also this PowerPoint presentation. So thank you. And if you all the speakers will stay a while here, we can close this session together. Okay, thank you.
Thank you.
Thank you.
Thanks.